So in earlier case, when we solved the question, I have directly used this formula. Actually, it was derived from this work done per second. They have taken the discharge that is in a radial direction where wire velocity will be taken as 0, and that's how we got this work done per second formula as this shown in this as shown here. So therefore, if we happen to find out the work done per second per unit weight of the water striking per second, then we will be using this formula, which is a similar concept that we have studied in the last class. And about the hydraulic efficiency and how we got this formula at the end, I explained it while solving the question. The next one is important term related to the Francis turbine. So the speed ratio and flow ratio is similar to what we have discussed. So they are using the same formula, but there is a variation in the value. For the speed ratio, it ranges from 0.6 to 0.90, and similarly from the flow ratio as shown here. And the only different thing here is they have given the ratio of width of the wheel to the diameter, which is given by n, and the value will be ranging from 0.10 to 0.40. So with this, we will be moving to the next one, the question, but there is some mistake in this question, so let's refer it from this figure. So the first thing they have given in this question, I just want to give the hint to solve this question, since it has the similar procedure like what we have solved in the earlier question. So therefore they have given like the overall efficiency as 75%. We can take it as 0.75, and the other thing information is they have given the peripheral velocity. So about the peripheral velocity, you can take it as a initial velocity of the plate, that means 0.26 root of 2gh. So another is the velocity, flow velocity they have given, which is 0.96 root of 2gh. And the extra thing they have also given the speed here, right? That is 150 rpm. And the extra thing they have given is the hydraulic loss. The extra thing they have given is the hydraulic loss, which is 22% available energy. So, and the next one is we know that, so we have to take one concept of like hydraulic efficiency, just take it in such a way that the total heat, let's take it as a total heat at inlet. Since they have given the hydraulic loss, let's take the hydraulic, subtract this hydraulic loss. And then take the total heat at inlet. So from here we can write it in 0. Since it is 22%, then we can write it as 0.22% and the overall heat. So this is the hydraulic efficiency, and from here we will get the value as 0.78. And we already know the formula for hydraulic efficiency from the earlier equation, that is U1 divided by GH. Just substitute this value here, and then you can solve the question. And the first thing that you have to determine is the guide van angle, right? Guide plate angle, I mean. And the first thing you have to determine is the guide plate angle. So for that, you will be using the formula that we have used in the earlier question, I mean. So the first thing you have to determine is the guide plate angle. So you will be using the same formula. The second one you have to determine is the wheel van angle at the inlet part, which is given by tan theta, and you will be getting it as VF1 divided by VW1 minus U1. So So you will be getting the value using this equation. And the third part is like diameter of the wheel at the inlet. So for that reason, for that case you will be using this equation, that is pi d1 and divided by 60, and you will get this diameter. And the next part is the part 4, that is determining the width of the wheel at the inlet, that is p1. We have to determine this p1. For that reason, you will be using the overall efficiency formula. You have the value, right? That is 0.75, and use the formula of the overall efficiency, and then from there you will get the discharge. You will get the value of the discharge. After getting the discharge, then substitute this discharge value in case of d1, b1 times vf1. So from here you can get the value of it. The next type of turbine we will be studying will be the Kaplan turbine. So this is like another type of reaction turbine which are applicable for the low heat, and unlike the Francis turbine, this Kaplan turbine will have an axial flow. So actually when it takes the water from the casing, it will be taken in such a manner which is similar to that of the Francis turbine, and then it will be taken out through draft tube like similar to that of Francis turbine. But in between, when the water falls onto the runner blade, it will be in the axial direction. So which means like the absolute velocity of the flow will be parallel to the axis of the turbine. And other thing is, water that has been taken from this guide vane will made to pass through this chute, so that it can distribute equally among all the runner blade. And other thing could be the guide vane mechanism, where it will control the position of the guide vane to determine the amount of water that is entering this runner, and leaving the runner. And while designing for the Kaplan turbine, it is actually done in such a way that it will have a wide range of operating condition. So therefore, the rotating blade, this blade which will be rotating around, will be experiencing like relative velocity which will be inclined or at a certain angle depending upon the velocity of the blade. And it will also have like absolute velocity which will be in the vertical direction. So therefore we can say that this, if we just observe in this figure, this blade has like twisting moment. So we can say that the inclination of the relative velocity at this root will be less compared to the inclination at the tip, because depending upon the velocity of the flow. And for the Kaplan turbine, if we just observe that the angle of attack will be optimum throughout. So when the water hit this runner blade, the angle will be always optimum. The angle of attack will be always optimum. They are being able to maintain this optimum attack of angle depending, because there is a continuous twist in the blade from root to tip. From this root to tip there is a twist. We can see here, no? That's the reason they are being able to maintain the angle of attack optimum. For the Kaplan turbine, they are being able to maintain the angle of attack. And if we just observe in this figure, we can see that starting from this root to the tip, there is a continuous twist in the blade. So that's the reason they are being able to maintain the angle optimum throughout. And other thing is about the pitching of this runner blade, which means like the positioning of the runner blade. Since the flow will be varying for different guide depending upon, since the flow will be varying depending upon the guide vane, so the relative velocity will change at the same time as well. If the ratio of flow velocity is very high, let's say, then this obvious like the relative velocity will be more axial. That means while positioning this guide angle, it has to make sure like it is somehow vertical. Even if there is twist, it should be in this. So, and other thing is, so in case of Kaplan turbine, the flow condition can be keep on varying for depending upon the guide vane. So what we can say means, if the ratio of flow velocity is very high, that means we can see this relative velocity will be more axial as well. So it will be more axial. That means since we have more idea, know that the guide, the the blade are, since we know that the blade are adjustable, we can adjust the blade in a vertical direction as well. So it will be moving a little bit further, and so it will be here like this. The placing of the guide will be vertical depending upon the maximum ratio of the flow velocity. And just in case if the flow velocity ratio of like the flow velocity is very low, that means the relative velocity will be more tangential, that it will be inclined at certain angle. So in that regard, you will be making this flow in the tangential way. So that means the placing of the angle will be more tangential. This basically explains about the positioning of the blade, which is also known as pitching. That means pitching of this blade depending upon the flow rate. That is vertical blade of pitching of the blade, or like inclined pitching of the blade. And other thing about this Kaplan turbine is in the axial flow reaction turbine, the shaft is vertical. So we can see here, you can see the vertical shaft here, and at the lower end of the shaft there is a larger surface shaft area, which is known as a hoop or a boss. So, and the turbine blade, if this van angle are adjustable, as mentioned earlier, it is adjustable, it is known as a Kaplan turbine. And if this blade angle are not adjustable, it is known as a propeller turbine. If it's not adjustable, so the next thing we will be talking about the cavitation, which is very important in case of Kaplan turbine. So if you just observe in this figure, when the moment the water enter from this casing, it will have a high pressure. However, when it's taken out from the draft tube, it will have a low pressure. That means throughout this journey, like the water will be having a low pressure. That means there will be a formation of cavitation. Cavitation means the water vapor bubble formation when there is a local pressure in that region is dropped below its vapor pressure. So it will make the materials erode, and there will be pitting as well, and erosion of the materials, and due to the damage in case of structure, there will be vibration. And let me give you one homework, like how to prevent the cavitation. Just make note of it here. And these are the some important point for the propeller or Kaplan turbine. Unlike the Francis turbine, so the velocity of the blade will be given by this equation, where d out is the outside diameter of the blade, and you might have noticed it in this figure. The outside diameter is given by d naught, and the inside diameter is the dB is the diameter of this hoop. And velocity of the flow at the inlet and outlet are equal. So, and they have given the area of the flow at inlet and area of the flow at outlets as well.